Welcome to the Tech Talks Daily Podcast, where you can learn and be inspired by real-world examples of how technology is transforming businesses and reshaping industries in a language everyone can understand. Here is your host, Neil C. Hughes.
Welcome back to the Tech Talks Daily Podcast. Now, I know what you're all thinking. What is he going to be talking about today? Well, after reading how next generation connectivity is powered by communication systems like 5G and how it's all set to radically transform all industry sectors, combined with the fact that it could impact global GDP by more than $2 trillion by 2030, I thought that would be a fitting topic to explore today. And that journey led me to a company called Ansys, and they are the leader in engineering simulation technology, and they provide multiphysics simulation solutions leveraging high-fidelity physics that span a scale from silicon to the city. And just saying that out loud reminds me of Keanu Reeves going, whoa. So buckle up and hold on tight as I beam your ears all the way to the US, because I've invited Larry Williams, Director of Technology at Ansys, onto the podcast today to talk about all this and much more. So a massive warm welcome to the show, Larry. Can you tell the listeners a little about who you are and what you do?
Well, thank you, Neil. Yeah, I'm a distinguished engineer at Ansys. I have over 20 years in this area of simulation, engineering simulation. My background, however, is in electromagnetics. I hold a PhD in electrical engineering from UCLA, and my sort of expertise primarily was in high-speed electronics, electromagnetic fields, antennas. But since then, at Ansys, we do all sorts of advanced physics-based simulation. And so my role has expanded to cover more physics and also to work with leading companies to apply simulation in driving their design and efficiency and product reliability. And then also I contribute to the strategic direction of our products and portfolio.
There's a lot to unpack there. I'm looking forward to diving a little bit deeper into that. But before we do, can I ask that you share your origin story? I mean, where did your passion for tech come from? And ultimately, what put you on this path that you're on today?
Well, I've always, ever since young, I always was engaged in electronics experimentation, maybe driven by my father, who's also an electrical engineer. I began my career in the aerospace industry in Los Angeles, and I was involved with advanced airborne radar systems, phased array antennas that are used in jet fighter aircraft. And so there's a lot of detailed design, and I hesitate to say how long ago that was. It was a while back. But in those days, there were lots of challenges in designing such hardware. And studying the electromagnetics at UCLA, I learned that solving the wave equation, which is what we use in electromagnetics, solving that analytically is a challenge. It requires pages upon pages of advanced mathematics. And in aerospace, I'm working, and then I see this product come in called HFSS. This is this high frequency structure simulator. And now it could solve any 3D geometry on the computer, solve for the behavior, be it a high-speed signal on a printed circuit board or some interconnect or a microwave subsystem or an antenna. And I immediately knew that, wow, this is a juggernaut, because I knew how hard it was to solve these things analytically. Now there's this product that could do this. And I watched as our R&D efforts in aerospace changed from a cut and try method where you build a bunch of hardware and go in the lab and measure it, to optimization on the computer instead. And that all happened within a very short time, within a few years. And I knew I had to join the company to get on board with what I knew was going to be a revolution.
What a great story. And for a lot of people listening, they'll be hearing about Ansys for the very first time. And a lot may think that they've never heard of you guys. But I read a great quote where I think you said that if you've ever seen a rocket launch, flown on an aeroplane, driven a car, used a computer, touched a mobile device, crossed a bridge, or even put on wearable technology, chances are you've used a product where Ansys software has played a critical role in its creation. So can I ask to introduce listeners to what Ansys is and what kind of problems your tech solves?
Yeah, so our foundation over 50 years ago was in numerical simulation on the computer of various physics processes, and we were primarily known for what we call structural analysis. So it's a mechanical engineering. You're looking at stresses and strains in a structure. How does it bend? How does it change shape? How does it operate? You could think of something, say the suspension system in an automobile, right? We've got all sorts of components there, and they're placed under various loads, and they may stress, they may change shape. You'd like to optimize the behavior of that system. So that's structural. But we do lots of other physics, fluid dynamics. So, the design and simulation of, say, airflow over an aircraft wing, or a jet engine simulation and design with fluid dynamics, or industrial mixing problems, and understanding how products are made in an industrial process. And then, as I've mentioned to you already, the electromagnetics, which was nearest and dearest to my heart. But the idea is that we could design a product or subsystem or system on the computer. So if you have you build a model, build a CAD-based model, computer-aided design-based model, the geometry, the shape. And then we can then apply various boundary conditions to that problem and then launch a simulation. And now the computer goes out and does the work and computes with great fidelity the behavior of these things in basic physics. And so that's the core of our business. We've expanded over the years to go even beyond. We now do things like photonics or optics, and then products just have become so much more challenging to design. There's so much going on where we need to include not just one physics but multiple physics. Say a device that both passes, say, an electronic signal, but also gets hot. What happens when those two physics are happening together, and how does the product behave? We have to look more at entire systems these days, because organizations that are designing a product, they need to make certain that it's going to thrive in the real world application. And then, because products are becoming increasingly more sophisticated, they have a lot more electronics embedded and embedded software. So Ansys, we've built out our portfolio in a very large way to handle all of those things. So core physics at the foundation, but then system behavior, bringing those models together, embedded software. And now once you can do all of that with high fidelity, then you can tackle higher level challenges, like challenges you might find in aerospace or in automotive applications or healthcare.
And before you came on the podcast today, I was also recently reading that next generation connectivity powered by communication systems such as, let's say, 5G will radically transform all industry sectors. And the impact of that could actually boost global GDP by more than $2 trillion by 2030, which is just incredible. But can you expand on that? And if there's anything in particular that excites you and your team at Ansys about the road ahead there?
Sure. At my core, I'm an engineer, and I like to work with engineers to design and help them design their products. And I think they genuinely accelerate their process by being on the computer. And so when it comes to the 5G opportunity, that's my greatest sort of enthusiasm, is what we can do for those companies that are providing the hardware that will enable that future. I know that you've had other guests on the podcast that have worked to look at edge computing and how the impact to society. We are, of course, very involved with that, but at a very fundamental level, we like to solve those engineering challenges. So you can imagine for 5G, we're looking at altogether new and higher frequencies. So that becomes a more challenging environment. There's more interaction in the environment, what we call multipath, challenges. There are diffraction challenges. We can calculate all of those things. So you can build, if you can imagine. You want to have say an automobile driving in an urban area where there's buildings and such, and you'd like that automobile to have fine connectivity to the 5G network. We can calculate all of that. We have various numerical methods that can say, well, what's the field propagation throughout that whole space? And how do we handle that? Of course, it also, there's all sorts of other aspects. You have an antenna that's mounted in a handset or a tablet or mounted to an automobile. How does that antenna integration work? Do we have sufficient radiation and reception for all environments? And then there's the infrastructure. One of the foundational tenets of 5G is just moving a ton of data. Yeah. So we're moving a massive amount of data. That includes, of course, building out these data centers. Our products are used, simulations used for all sorts of electronics, from the semiconductor devices to the IC packaging, the printed circuit boards, even the entire data center itself, for cooling, for high-speed data transfer on those printed circuit boards, large printed circuit boards that are used in networking equipment. And so there's lots of areas for us. One you might find also interesting is it's all the physics is involved. We think of 5G and you think of the high tech, but we're going to place a lot more microcells out in the environment. We're going to place them up on light poles and such. One of the big telecom companies says, well, we're very interested also in understanding, the mechanism by which we clamp our microcell to one of these lampposts. And they wanted to understand the durability and strength required. They wanted to minimize the amount of material being used. And so it crosses all sorts of domains where we contribute to 5G.
And you guys are also providing comprehensive simulation technology that is helping automakers tackle autonomous vehicle production and safety challenges. And what really stood out for me was you do all that, but without the need for expensive prototypes or countless hours of test driving, for example. But do you have any use cases that you could possibly share that would just bring that story to life?
Yeah, that's a very exciting area in our business. We do focus on autonomy. And we have products it takes multiple physics, multiple solutions to come together into our product for simulating autonomous driving, especially. I think it was interesting. Famously, the president of Toyota at the Paris Auto Show a few years back said that it's estimated that it'll take 8.8 billion miles of road testing before we could ensure the safety of an autonomous vehicle.
Wow.
You say 8.8 billion miles is going to be impossible. How do you do that? Well, there is one way to do that, and that is to simulate it. So we have tools that can simulate optics, electromagnetics, and I think your listeners will know that an autonomous vehicle has three main modalities for sensing the environment: a camera, radar, and something called LiDAR, which is we use a light beam to send a laser and do ranging with a light. Well, it's what's nice about having three modalities simultaneously. You integrate the information from all three. And so if the radar doesn't see something, the camera will, and vice versa. We simulate those sensors with extreme accuracy. You think about it, you're driving in an automobile heading westbound late in the afternoon, the sun's in your eyes as you're trying to drive. Well, likewise, the sun's in the virtual eyes of the camera. We simulate all of the optics inside the camera and the light sensor. So we have a real physics-based model of what the camera sees. And then we integrate that into a driving scenario. So we can now convert physical miles, those 8.8 billion miles that would otherwise have to be driven, we replace those with virtual miles. So we build out a system which has the embedded software, the AI algorithms that the developers of these systems will be working on, and then run lots of scenarios, thousands upon thousands of scenarios. Automobile driving in sunlight, driving at night, another automobile coming from onto an on-ramp onto the highway, persons in the field of view of the automobile. All of those can be used together and simulated together to really predict and tune the driving scenario and how we program these systems to drive. You may find really interesting one example that we've been working on with some of our customers in Germany. They were concerned about inclement weather. So just as you're driving in the rain, you get water droplets on your windscreen. Another car drives by and splashes your windscreen. We can simulate these things. It's fluid dynamics. So we have a solver called Fluent that can predict water droplets, how they will be applied to the windscreen of the car, how it will diminish the view. And then we use our optics simulator to look at what the camera sees and then use that in the overall driving scenario and then embedded software on top of that. And so it's really quite fascinating to bring together all of those physics to solve a very challenging problem. We do that all on the computer.
Love that. And so am I right in saying then that autonomy in the automotive industry, it can't happen in our lifetime without simulation technology? And assuming that is right, how would you explain exactly what simulation technology is to someone listening outside of the industry?
I liken it this way. We build a software product. And for those of your listeners who've ever built a software product, we have a group of software architects who develop certain subroutines and codes. They perform an analysis, they change what they may want to change in the code, and then they check it back into our configuration management system. We compile the code, and then we run regression tests. So we're out on the cloud, and we're running all these different case studies. Make sure we didn't break anything inside the software. If you change one small part in your simulator, in our case, a simulator, then we want to make sure it's still reliable. So we do that, and we do that very diligently, lots of regression testing. Well, it turns out for autonomous driving, the automobile manufacturers are doing the same thing. They encounter a new scenario, a person in a crosswalk in late afternoon. This is a scenario, another vehicle pulling up. They want to build a new algorithm to detect that. And they want to train these AI algorithms to understand that. Well, if they change anything in the code, they're going to have to do a regression test themselves. And what is that regression test? Well, it's those driving scenarios I mentioned to you before. And so they will run those over and over. And I think, really the simulation is really the way to solve these problems, because I just don't see us being able to do it any other way. You can't drive enough miles to really gain that confidence and drive the safety level where you need it to be.
And Ansys does work with over 45,000 customers worldwide, I think, and many of the biggest names in the automotive industry. But I'm curious, is there anything that excites you about the industry right now and how technology will continue to transform that industry into the future?
Well, we already mentioned autonomy, so that is an exciting area. Electrification, right? We see more and more electric vehicles, and we of course we can simulate electric machines, the motor inside an automobile, and so that's an area which is really, really hot. We were pleased to work with Lucid Motors. Lucid is a company here in the United States that is developing an all-new electric vehicle, very luxury vehicle, but also very high performance vehicle. And they were pioneers in saying, all right, in order to get a lot of energy out of a small space of the electric machine. We're going to have to keep it cool. We're going to put a lot of electrical power into this electric motor to propel the car and accelerate the car. But we also need to cool it because we're going to generate heat. And so they pioneered a method by which we would run a cooling oil inside the rotating electric machine. So they worked closely with us. Our engineers, we have a very broad, diversified group of application engineers who helped our customers. So Lucid worked closely with us to develop that system, and we did that simulation. And you may imagine it's very complicated. You've got oil spraying into a very rapidly rotating rotor of the electric machine, and there's air, and there's oil, and there's motion, and all of that has to be simulated with fluid dynamics, and then calculate how much heat is transferred to that oil and brought out. That was a pretty exciting area. In electrification, we also we worked. It was a couple of years ago. We did a really great project with Volkswagen. Volkswagen, they wanted to demonstrate their electric capability, and so they decided to build a race car to tackle Pikes Peak. Pikes Peak is this race course that winds up a mountain in Colorado, and the goal is to climb climb this hill and get to the top over this twisting, turning road as quickly as possible. And their goal was to beat the electric vehicle record up to Pikes Peak. Well, they not only beat the electric vehicle record, they beat all records. They were the fastest vehicle of any type to ever go up that mountain. And they did that with an electric vehicle. But what's remarkable about that is that they wanted to do it in a short order. So they had to produce, test, and race an all new electric car within 9 months. So we worked closely with Volkswagen to convert an existing internal combustion race car. They only had 9 months. They couldn't design an entirely new car. They took an existing chassis and then had to find locations for the batteries, find ability to get to charge those batteries rapidly, and also to discharge them. They go up that mountain in just 8 minutes. So they had to discharge all that energy in a very rapid order. So we helped them with the battery management system to make certain that they could model all of that. And it was a complete dynamic simulation. The vehicle goes into a turn, braking into a turn, then accelerating out of the turn, then braking into the next. We programmed all of that into a dynamic simulation, a system level simulation, to compute the amount of energy being used to optimize it. And so we, of course, it was their achievement, but Ansys, we did help with the simulations there. So we're pretty proud of that capability. Yeah, the other areas of automotive, as I mentioned, also 5G connectivity is important. I think autonomous vehicles are more effective and safer. Or maybe all vehicles with driver assistance and such would be safer with a bona fide connectivity to a network. If there's, I think it's possible in the not so distant future to be able to understand where, say there's a scenario where you have automobiles that are going to be at a crossroads on a highway. The driver may not be able to see a vehicle from another side street, but the network could know, and the network could know whether or not we think that car is paying attention and is going to stop or not. Well, having connectivity to the network, I think, could potentially have a great impact on safety. And so connectivity, I think, is a big area for automotive.
And we did mention rockets at the very beginning, and there is a renewed excitement and interest in space right now. So I'm curious, how do you see the future of space, and what are the benefits of these recent major advancements that we're seeing?
That space is very exciting. The traditional, development of a new launch vehicle would take on the order of at least 5 years to design and develop and ultimately perform launch testing. SpaceX comes along and says we're going to reduce that to 18 months. So that's a 300% improvement in the timing of how they could get to a complete system, and then they're simultaneously they reduce the cost of deploying, sending a payload into space. Their cost was reduced by a factor of 10. Now there's other ideas coming along. There's a company here in Southern California, Relativity Space. They want to reduce that. We said 5 years for the traditional design, 18 months is what SpaceX accomplished. Relativity Space wants to reduce this to 60 days. And they're going to do that with a 3D printed next generation rocket. And it's pretty fascinating. They built this giant robotic 3D printer. He has these large robotic arms that perform a deposition of metal, and they slowly build up things like the fuel tank, for example, of a rocket. And they build that up inside this with a high power laser and a wire feed. And the machine, frankly, is quite frightening. It's so big, but it can build rocket motors. They successfully tested last year one of their first rockets. So I think that we're pleased that we were able to work with Relativity Space and help contribute to their success in 3D printing of rockets.
Incredibly cool. And a question I'd love to finish on with you here is, what are the implications on the environment, infrastructure and consumer trust? And are there any major challenges that the industry is up against? Because we're talking about all the exciting things, but I don't want to gloss over the fact that there's probably a few challenges along the way too.
Oh, yeah. I think when it comes to the infrastructure, I would say that by our own nature, engineers, we look to optimize systems, and we want to make our products efficient and not too much wasted material and those sorts of things. And so, by our own nature, engineers we optimize things. By simulating it on the computer, you have an even greater flexibility. What an opportunity it is to try new ideas on the computer, because it's you get almost risk-free innovation and power to explore. You can try things that would not normally be tried before, and it doesn't require you to go out and do a whole host of prototyping and fabrication. You can try new ideas, and so we can build a more efficient automobile. We can work on more effective industrial processes, smart buildings, and simulating the effectiveness of various strategies for heating and air conditioning. And then, for anything that's sort of infrastructure, I'd say, if we're building a bridge, we can look at the bridge technology itself. Or, how are we placing the concrete, the reinforcement, the screw anchors, say, in the concrete. We can model all of these things on the computer. And in fact, there was a recent case where we did simulate screw anchors in concrete. And you think, well, what does that look like? You bore a hole in the concrete with a hammer drill, and then you drive what looks like a screw bolt into the concrete. And as it fries into that concrete, it ablates away some of the little bits of concrete that chip away. How do you simulate that? And we invented an entirely new simulation method called smooth particle Galerkin method, which can track all those little particles and where they're going, where all the energy, all the momentum is going, and faithfully predict that. So things like that are done on the computer, and we can build things safer with greater longevity. And then, just understanding engineers being able to meet design requirements, satisfy various standards. There's lots of safety standards in, say, aerospace or automotive. And we can do a lot of that prediction on the computer a priori and make certain that products are safe and reliable.
Well, I've loved chatting with you today. I've learned so much myself, but we started the podcast talking about your origin story. And what I'd like to do now is have a bit of fun with you and ask you, what was the soundtrack to that origin story? Is there a particular song that has accompanied you on your tech career or just helps you get your head in the zone before going on stage or going into a big meeting? Is there a song that means anything to you that we can add to our playlist?
Oh, there is. I would very much like to add to your playlist the Dave Brubeck Quartet, Take Five. Yeah. It's perhaps one of the most iconic, I think, jazz compositions. Now, I'm not a jazz expert by any means, but I do enjoy the song. But what I liked about it was that Brubeck, he liked to experiment with unique timing. And their drummer, Joe Morello, he wanted a new piece which would use 5/4 time. And so, and as a group, it sort of came together like this because Brubeck liked the idea. The drummer was promoting it, and then Paul Desmond, the saxophone player, wrote the initial pieces, and then they all put it together into this iconic song. It sold over 2 million records back in those days. And it was, what I liked about it is that they tried something completely different. Nobody was doing that, using this 5/4 time. And they knocked it out of the park. So they tried something novel and they delivered something iconic. They dared to be different and it paid off. So, I think that simulation is like that. You have the power to explore new ideas, try new things, and see if you can hit another home run. I think it was, getting back to my own story, I left a very nice job in aerospace to join a fledgling company, Ansoft, which was acquired by Ansys. So I'm, through and through Ansys. But I left aerospace to join a small company because they were doing something so remarkable and could solve any 3D problem that couldn't otherwise be solved analytically. And so I would have to say that Dave Brubeck's Take Five.
Great choice, and love the story behind that. I'll proudly add that to our playlist. But before I let you go, can you remind everyone listening of where they can find out more information about Ansys, the kind of work you're doing, or even contact your team if they've got any questions and want to carry on this conversation we started today?
Well, sure. Of course, we are available with our website at ansys.com. We're on LinkedIn, Facebook, Twitter, YouTube. The YouTube channel is great. Look up Ansys on YouTube and you'll see all the things I can only try to describe on a podcast, but you can visualize them. That's something that's so exciting. So you can see on our YouTube channel everything, every sort of application. So I would recommend that.
Love it. Well, I'll add that. I'll add a video to the blog post that will accompany this episode and all of those links. But more than anything, just thank you for taking the time to share your story today, the work you're doing at Ansys, and introducing everyone to the technology and understanding what simulation technology is too. Thank you so much for doing that.
Sure thing, Neil. I sure appreciate the time.
A huge thank you to Larry for sharing how tech is enabling solutions which are backed by the world's leading centre of simulation expertise, all aimed at providing customer enablement through technical support services and training and so much more. But for me, it's how simulation can address those increasing challenges faced by those engineering the future of 5G and delivering that significant competitive advantage. And I love the fact that, once again, we're exploring something where we're surrounded by technology every day. But I suspect that before listening to today's podcast, you might not have heard of Ansys. But as Larry said, if you've ever seen a rocket launch, flown an airplane, driven a car, used a computer, touched a mobile device, crossed a bridge, or put on wearable technology, you've probably used a product where Ansys software played a critical role in its creation. And again, that's one of the big reasons I record this podcast every day. So every day is a school day. I hope you enjoyed it as much as I did, but keep your insights coming over. techblogwriter@outlook.com, Twitter, Instagram, LinkedIn at Neil C. Hughes. And we'll do it all again tomorrow with another guest and a completely different topic. So all that's left for me to say is a big thank you for listening. And until next time, don't be a stranger.
Thank you for listening to the Tech Talks Daily Podcast with Neil C. Hughes. Remember, technology works best when it brings people together.